Good. So, Petri is going to talk about the Dirac equation and the dynamic universe. Don't know how it follows with what you did this morning, but I assume there'll be links. And and after that, Chris, then we'll go more to the quantum physics part, although with the Dirac equation with the...
It's a Dirac equation, isn't it?
Right? Yeah, but that's a different one.
It's the Dirac equation.
The children at the back.
Yeah, I know. Children at the back be quiet.
All right, welcome back and thank you. Welcome back to these discussions and I think now we have quite a lot of time here in this session. So let's make it so that I make some short stops at some points and then we can discuss. So it's not only that we have a long discussion at the end, but we could have like small discussions. So I'll start with this like introduction to general relativity by Foster, and I think the first image in that book is this, and it's quite easy to understand. There's like gravitational field and electrostatic field. And even though things are usually expressed as Lagrangians, it's still quite common to use forces and accelerations as like schematic depictions of what is happening. And we can sort of conceptualize that the GR and the metric is involved in gravity, and then the standard model included the quantum electrodynamics, which the Dirac equation sort of is part of, is in this electrostatic field. So now to think about these things and really like simplify things, I'm considering here to think two kinds of concepts or states. There's the like matter at rest, which is sometimes called like pure time light. Like what does it mean to have matter at rest? And then light like space-time trajectories. So on that, what does it like? Those are like two like sort of complementary ways. For example, how light interacts with matter and vice versa. And now the thing that I'm sort of bridging myself to Tuomo's ideas is this from the review of particle physics, the equivalence principle, that the first aspect of the equivalence principle is that the outcome of a local non-gravitational experiment referred to local standards should not depend on where, when and which local inertial frame the experiment is performed. This means, for instance, that local experiments should neither feel the cosmological evolution of the universe, so constancy of the constants, nor exhibits preferred directions in space-time, so isotropy of space, local Lorentz. And also, of course, here there are a lot of like questions like how Tuomo's ideas will work out. But what I suggest, or even what I think that might be happening, is that you can concentrate here on this refer to local standards. What does it mean, refer to local standards? So local standards of second, meter, kilogram, also the electric constants. And that might be one way of conceptualizing this constancy, in a sense that the standards themselves can be evolving. And maybe we could find ways to think sort of outside the box about the standards themselves, so that they wouldn't be like just assumed to be there, but they are like physical standards. And we are in difficult position because there's, for example, already in the 70s, the Weinberg wrote the quantum theory of fields, 2 volumes and 3 volumes actually. After that, gravitation cosmology, and then there's the Wisner and Thorne and Wheeler famous book. So, and these haven't changed so much. So they're still like valid. So how many of us like know these so that we could make progress in these discussions? I also this is from the review of particle physics. So it's a general relativity in a nutshell, in a sense, because there's only a little bit more than one page, and there's their depiction of general relativity as gravity as universal deformation of the Minkowski metric. And then they have this action, and there's this Einsteinian Lagrangian and standard model Lagrangian, and then here at the bottom, here's actually the standard model Lagrangian with Higgs terms and coupled with gravity. And it's a difficult thing because for example, Tuomo has intuition that maybe gravity and electromagnetism might be related when the space is turned 90 degrees at itself, so in that Clifford algebra sense. So then it would be perhaps this Faraday tensor construction here. But how would we proceed? So one way to proceed is to simplify. And this is a wonderful presentation by Richard Behiel about electromagnetism as a gauge theory, and he has provided these sources, so I dare to use his depictions as a base material at this first part of this presentation, but it's quite solid work. And there's the Lagrangian of quantum electrodynamics. So there's the free Dirac term. Well, it's free if it's free, the electrokinetic and mass energy here. Then interaction energy. So this psi couples to photon field, or he calls this vector potential photon field. And kinetic energy of the photon field, which is like this Faraday tensors here. And then through normal like Lagrangian mechanisms, you integrate over space and over space-time, and this Lagrangian density to get the action, you vary it, and the physical trajectories of physical thing is what is just called the stationary action. So better would be if we could discuss like photons and this vector potential and these electric and magnetic fields here, but we could now simplify this in a sense that think about the state of rest and light. So we could go towards this sort of state of rest here in the Dirac term. And the Dirac equation is here embedded. It's multiplied by C to get the energy. So here's the Dirac equation. And the psi is this kind of a bispinor at each point of the spacetime. So there's like 4 complex numbers. And here you already see the energy momentum relation that Behiel like emphasizes already at the beginning. An important thing or interesting thing, at least to me, algebraically, is that we can take one C out of that equation, but in a sense not the other, because other is included there. I have now marked these with different numbers, C0 and ZR. CR, because in Suntola framework, the metric is somehow encoded into the speed of light, in a sense. So the gravitational effects and the gravitational time dilation is encoded by varying the speed of light. But locally, because the SE system is defined so that the proper time is defined for all local spacetime patches, and locally the speed of light is still constant. But this is already like interesting because now there's this like momentum, sort of momentum is like Euclidean momentum is like a fundamental thing, and you then just multiply it by C to get to the energy, and this is it just doesn't transform as as Lorentzian in this setting, because the terms are on same side. And then if you continue this Dirac equation, you have this covariant 4 gradient, and this is also interesting that the C could in principle be in the time in the t, and this would be totally like space-like derivative in a sense if we ignore the signatures there. And now there are these gamma matrices, and now we could bring in some Clifford algebra to structure those gamma matrices. There's many ways to give structure to these gamma matrices. So what are they really about? And we can't answer it here, but we could perhaps find a representation that somehow could communicate with dynamical universe idea. And the gamma 0, gamma naught will be key in here because it's the time-like Dirac matrix. So to quick introduction to like basic Clifford algebras is like you have scalars, and then for example here you have 3 orthogonal vectors. So this is not like 3-dimensional Clifford algebra. They are like directional line elements. And here I have just defined them all to square to 1, and they are all mutually anti-commutative, so they are orthogonal. You can multiply them further to get bivectors, which are like directional planes or rotors. This is just a shorthand, so E1 times E2. Thanks. E times E2, and you can, using those Clifford algebra relations, you can get them. Sorry. And then there's trivectors, which are like volume elements. And this is also E1 times E2 times E3. And now you are in closed algebra. So you can't get out of this. So if you start multiplying them together, for example, E3 to this E2, 3, E3 times E3 is 1, so only E2 remains. So this is like closed thing. And this is interesting because this is like a Pauli algebra, and especially if you multiply this with itself, you get -1, and this commutes with all the elements here. You can try it out. So you can put it at all places. So actually this commutes with all the elements. So this works as an imaginary element in this algebra, but only this algebra. So when you exponentiate this, then it starts to oscillate between this and scalar. And in some parts of those Dirac algebra, like wave vector formalisms, the imaginary element, when it's in exponentiate, it actually might mean, in some settings, this kind of oscillation between scalars and volume elements. And then there's quaternions as the even sub-algebra here. And there's also this unipotence that one can use. So they square to they stay the same if you square them, and they mutually annihilate, and there is sum to unity. But they are important elements in Clifford algebras. But now to come to dynamical universe, you can extend it, for example, with new orthogonal direction E0. And at this point, I define them all to be just square to 1, and you can multiply them together to get these kind of interesting new like bivectors, new like planes in a sense, like rotors between this zeroth and spatial dimensions. You multiply them further, you get these 3 like extra volume elements in addition to the normal one, and then you get the pseudoscalar of the algebra, this kind of a hypervolume element. And this actually squares to 1, I think. And this is now the Clifford algebra or geometric algebra, as it's sometimes called, G4. And there's this important idempotence 1 plus minus E0. So because you can rotate the coordinate system how you want, you can always like select E0 to some interesting point and develop around it. It's an interesting concept. But also you can use this hypervolume element because this squares to 1. So you can also use that, and that some people, I guess here the audience also are familiar with that.
Petri, I just
Yeah.
wanted to say, if anybody forgets this equation down here, it's tattooed on my arm, so you can remind me. 1 equals, yeah.
All right.
Give Clifford give it to Clifford.
Yes, and then interesting thing is that you can select different kind of basis elements as the generating elements of your algebra. So, for example, you can select these which are between this zeroth and ordinary vectors as basis elements combined with this E0, and this is called 1.3 because there's one like ordinary like time-like, let's say time-like vector, and then the rest square to -1. And this is like close to Dirac algebra. And you can then switch between these in a sense that you can multiply by E0 to get rid of this E0 here, and then it switches to Pauli algebra where there's only scalars and these. So there's sort of really deep features of this. And also these Dirac matrices, they are these 4x4 complex valued matrices, so there are different representations of them. This 4.1 is maybe common, but most common, but there's 2.3 and 0.5 to 0.5. And now I tried to make the representations or study the representations in a quite standard fashion. So this gamma 0 can be conceptualized as E0, and then this E1 0 as gamma 1, U0 as gamma 2, and E0 as gamma 3, and they actually work out. So they are the correct in the Dirac representation. They are the correct matrices. And now if you multiply these out, so there's this pseudoscalar where there's all the gamma matrices are together. There's this volume element. You get the fifth gamma matrix, and this is related to chirality in particle physics. But this might give an nice, perhaps nice geometric view to somebody what the fifth gamma matrix is about. It's like this kind of a like volumetric element, but there's this I. And these are then the representations of these like space-like matrices. I also calculated here what the volume element is. It's this kind of symmetric thing, and then this 4-dimensional volume element is like this. But these are difficult, these charge conjugation matrices. Why are they like that? And you who are familiar with particle physics are more familiar with this. These are also so-called nullpotents that can be used to generate these things. But let's not go there. I will shortly so. Or maybe we could actually, I will read this aloud and then we could have a small discussion. So here's how Antoni Leisenby describes these gamma matrices in one talk. Antoni Leisenby is a well-known figure in Clifford algebra and geometric algebra communities. And in one lecture he said this aloud. And again, this is quite interesting idea that as human beings, we are not used at all at the idea that we are actually shooting along a time axis at the speed of light. At any moment, that's what we are primarily doing. We are moving extremely rapidly up the time axis. He means this gamma 0, this C0. And so these vectors which we have around us, Cartesian basis vectors in this room, are actually being swept really rapidly. And so it's a very interesting that in the 4D way of thinking about that, they are bivectors because that's sweeping out, but coming back down the other way, we can use the gamma naught to define these things that are actually vectors for intensive purposes in this rule. So if you multiply this by gamma naught, this becomes scalar 1, this becomes E1, E2, E3. So I think maybe you have some like ideas or like what kind of thoughts this gives, that you interpret the gamma matrices as that kind of like expansion direction in a sense. So the space is expanding in the direction of gamma naught. Or we can keep it.
I'll say that the modern view. So I spend all of my life on geometric algebra now, and the modern view that this is very foundational to how lots of people see things, with one exception, which is that at the bottom he says he's said two words that are from his point of view the right way around, but are from my point of view slightly the wrong way around. Because here would be the argument: what is a reflection in space? You know, you can imagine having a mirror plane in front of you and you see your reflection. And if you imagine yourself in the past, you also, 2 seconds ago, you were also looking in a mirror. So you saw yourself there as well. So this mirror is also swept through space. And if you ask, any matrix is a transformation, right? It's a linear transformation. And what linear transformation do the Dirac matrices do? Well, the modern thing, coming mostly from this guy Stephen Dekennick, and John Selig and other people, but anyway, they would say that vectors are reflections. So they're the planes, and they're planes that are being swept out over time. And then it's the bivector that is the intersection of two planes. And yeah, we would say it that way around in the modern world. So yeah.
Who was your quoting
So this is Stephen Dekennick. Dekennick, yeah. He's he's not so well known in physics, but he's one of these people that's very important in getting computer animators to use Clifford algebra. Yeah, very interesting guy.
So is it in the projective?
Yeah.
Case?
Yeah.
Okay, so it's a slightly different geometric algebra, but on a different basis.
But you could take the same geometric algebra that Petri has said here and apply the same logic to it. You just wouldn't move away from the origin. So you wouldn't incorporate spatial translations, but you would incorporate vectors and bivectors. Yeah, and they would be the Dirac matrices, which is to say that they would do reflections in space-time, both space-like reflections and time-like reflections. Yeah.
Very good. Then let's continue. I will go this really quickly because I want to go to the standards question if you have time. But the exponential function is really fundamental, and you can divide the even and odd terms differently. And then you can try different elements. For example, unipotents have these hyperbolic geometries. Imaginary elements, or these kind of vectors which multiply to -1, are Euclidean geometries. Then these nilpotents, they square to 0. So it's really like this kind of a parabolic geometries, really like simplifies things, but they are in between. And then the idempotents are really, I'm not sure about this, does it go? Because it's how do you define this lower, like a to 0? Is it still a? So but still those are like interesting, because when you are exponenting matrices, then you can interpolate between different like geometries and different objects depending on for example the eigenvalues. And then just to show like how sort of deep these things can be. So for example, Sobchuk has developed this kind of idea where you have nullpotents A and B on odd plane, and then their products sum to 1 on even plane. And through these, you can get the matrix representations that actually encode, works as a basis for this whole like system. And then you can find like polymatrices, and this you can make like a complete structure, complete algebra around here, where these nullpotents are like sort of between the other elements. And this is like a really like some people are really good at this kind of manipulation, and you can also extend them. Sobchuk has shown how you can extend this indefinitely to like this odd even dimensional matrices. And then, as a inspiration at this point, in the Begier video, there's this 4 dimensions CT again, like sort of like expanding dimensions, and then the Faraday tensor has these curl like fields, and he also shows these kind of symmetries that might resonate with some Clifford algebra people, how the Faraday tensor is how the electric fields and magnetic fields, how they are like dual to each other. And also in the latest advanced work, for example, Antoni Leisenpyy has used octonions, and there are also similar kind of things where the pseudoscalars work as a central elements of the algebra. But now back to this Dirac matrix. So you can actually you can think of or simplify it, or study a simplified version where you have free particle with momentum 0. And this is the Dirac equation now opened up. So there's the gamma matrices work as a like coordinate axis sort of, and then 0 momentum eigenstate is so that these gradients are 0. So then it's a really simple, this kind of a sort of like time-like equation, and due to the representation how the gamma 0 is, it actually splits into two parts. So this is often called matter, and this is antimatter. And now here is the one that I want to stay a couple of seconds, because now the electron has this solution, and positron has this solution. So this is something that now is fundamental here, because this mc squared divided by h bar, it's now like a Compton frequency. And you can calculate it. It's like, hopefully I calculated it right, so it's 10 to the 20th hertz. So there's in Dirac, and I guess in quantum electrodynamics also, there's this kind of like 10 to the 20th hertz, like fundamental frequency, because these are natural constants. So there's this kind of fundamental frequency. And now, for example, when we study gravitational time dilation, there's a really interesting question, like what happens to that like fundamental frequency? Does it really like actually go down or decrease? Does it increase or decrease? What you actually see also on greater structures, such as like hyperfine transition of cesium atom, which the atomic clocks are based on. And with Tuomo's ideas, then you can take one C out. He thinks that there's one C in H, so there's mc divided by H0 is this fundamental frequency in a sense, and it's you can derive the Compton wavelength and now here also, if you think the Compton wavelength in terms of this wave number, I might have missed 2 pi there. It's usual when radians and frequencies are involved. But in a sense, you can take one C out here to T. So then the CT is again a space-like dimension, not space-like, but like metric dimension. And then the MC divided by H is then this kind of a wave vector. So it actually could encode this kind of like wave in this gamma 0 like direction at rest, because we are at rest. We are the electron is at rest, but it's like because the gradient is 0, so then it's everywhere. but still, so there could be this kind of like fundamental like wave going on. And one can also here see that there's this like 3-sphere structures in a sense, because this normalization condition means that these complex numbers here, their magnitude sum to 1. So actually this is a quaternion thing. So there's a like double quaternion when there's a bispinor field. And then he also shows how the spin is in its like most basic level in a sense represented in this kind of frameworks. And I don't know if maybe we could do you have ideas about this? What are your comments about this?
I mean, are you just simply connecting Clifford algebras with the Dirac algebra? Is that what this is? I'm not quite sure where we're headed here.
Where we are eventually.
Yes, he's doing, I think.
Yes.
Wishing to tell Hamish what he's doing. I thought that'd be the kind of thing that Hamish would be up to, wouldn't it, Hamish?
Yeah, yeah. I mean,
Cool.
this is fairly, yeah. This seems to be, standard.
Yes,
Yeah.
it is. Yes, it is.
Okay.
It's just it's kind of like emphasizing this idea.
Huh.
Yeah, emphasizing this idea that there's this kind of fundamental frequency, and you can interpret this as a wave vector at rest. Because it's interesting for yes.
There are remarks we made earlier quoting Lazenby that provoked Hamish's intervention to say that they look at things slightly differently these days. It seemed to be leading up to something, but I wasn't quite sure where. You were saying that Lazenby stressed this point that one should think of the structure in terms of proceeding at light speed on the cone and the Cartesian corners.
Yes.
Now they're all being swept along inside it. I mean, I see that, but where was that leading? What was what's the point? What was the point he was making specifically in drawing attention to that?
I think in context, he was just talking about how you've got a space vector and you've got a time vector.
Yes.
What's the thing that's over time?
Yes.
And his answer to that is a bivector.
Yes. I see that.
And,
I've got the answer.
And that's sort of, well,
Yes, it's the bivector that is sweeping. It takes in that encloses the fact that you are moving at light speed.
you've got both.
You've
You've got the spatial thing and the time-like thing, and we would say that is nice to have as a. You don't want to just have the vectors. It's nice to have these things made out of vectors.
Yes, indeed.
Yeah.
And I think it's possibly connects also with this idea that there is this kind of process metaphysic influence behind some of the instructions in Clifford that Baseline was very interested in.
There's the danger of this approach, in my opinion, is that you're inputting time as a vector, which is fine at sort of a certain level. But the point is that time, firstly, does not act like space, because as far as we're aware, you can't go backwards in time, so it's not strictly a vector in that sense. You can only go one way. But also, we also know through entropy and other physical attributes that time has more of an evolutionary principle to it, a character to it. And so I think that just by making it a vector, which is fine, and I understand what you're saying, so I'm not quibbling with that, but I think you have to be a bit careful, because the nature of time is not as simple as is being placed here in this very, in that algebraic context. Well, I know we do it, I'm after it all the bloody time, so I'm not saying that I'm somehow superior or something, but you have to bear in mind that time is definitely really not a vector. It's something more than what is, I don't know, but
Sorry, because there's this aspect of becoming which is not there in the case of the spatial.
Yes.
Yeah.
Yes.
No.
Yeah.
That's-
Sorry, just 1 minute, and just to respond to Mike. Yes, you're quite right, and that's what I'm getting at.
Yeah.
It's more of an evolution. I think of it evolutionary wise, but we don't know the answer. But be careful. That's what I'm saying. because treating it just as a vector can lead you down the garden path a little bit.
So, absolutely correct that obviously thermodynamics forwards in time, not the same as backwards in time. In the context of, in the limited context of the Dirac algebra, and also, what would you say, Lorentz boosts. Yeah. So thinking about Minkowski space, or thinking about the Earth rotating around the Sun. Many systems are time symmetric. Not all. In many of my favourite systems, like my wife,
If you do a particle physics lectures course, there is actually one lecture which is almost totally on about how you arrange your Feynman diagrams so you don't run into this problem. So I'll be again.
Peter's wanting to move us on.
No, that's fine.
Indeed, no, because we have got 15 minutes left of the talk, and then we've got some time at the end. Thank you.
Yes.
Yeah, except
All right.
if you want to answer to some of the points.
No, I think it was good discussion, yeah, about that. So then I'll go towards those standards. So that is a really fundamental thing. That this is, for example, the review of particle physics, the physical constant that starts with C, all right, and here also these are constants. You don't mess up with them. But then again, let's look at these referred to local standards and general relativity, because there is a possibility to study the Schwarzschild metric. And the Schwarzschild metric is an exact solution to the Einstein field equation. So if you crunch this out on supercomputer around a single mass, you ought to get the same equation. And here, this is the ordinary two-sphere metric here, but then the Schwarzschild radius and this time-like coordinate time, and then the proper time is here. So now you may disagree with this, but you could perhaps study like pure time-like space-time intervals by setting these to zero, these differentials here, and then you would actually get a relation between coordinate time and proper time throughout the whole of space-time around this Schwarzschild space. Because now, for example, dt is coordinate time, it's, for example, 1 second. Then the proper time is less, for example, half a second. And we could interpret it in coordinate time that the frequency has decreased because it amounts to less time-like intervals of this time. Yes?
Why are you cancelling?
I'm cancelling is that because I'm looking for pure space-time interval. So I'm putting these differentials to zero. Just at rest, sort of. In Schwarzschild metric, in Schwarzschild coordinate at rest. So in a sense, this creates this kind of let's call it gravitational time dilation throughout the whole of space, parameterized by this R.
Okay.
Yes. And now, if you increase this R, this goes to unity, and then the coordinate times and proper times agree. So a clock which is taken far away, it then records the coordinate time. But also you could increase this mass or decrease this mass, so generate more mass bring more mass in the center. So if you bring this to zero, then also this comes unity. So in a sense, you can compare between different points in space-time by not comparing them to each other, but comparing all of them to their coordinate quantities and making the comparison there. And this is actually what happens in Shapiro delay, for example, which is one of those tests of general relativity. And now the speed c is defined constant, and then the frequency of cesium is defined as this count. It's defined as that. And now in the proper SC second definitions. There's the definition of the second should be understood as the definition of the unit of proper time. It applies in a small spatial domain that shares the motion of cesium atom used to realize the definition. So in a sense, it says that this cesium atom frequency must have been decreased here in proper time in the gravitational field. And this might be one way to conceptualize, taking the standard seriously to conceptualize what is going on when we are talking about gravitational time dilation. And also, this you might disagree much more still. But you can take a light-like spacetime interval. A light-like spacetime interval is where the proper time is 0. So you put this to 0. And if you solve just algebraically here the dt, which is the coordinate time, you get this result here. And now if you study this, this is like ordinary two-sphere metric. But this here, it's like the radial distance has increased by this amount because this is the inverse. So the radial distance is longer by this term. And then also the speed of light has decreased by this amount. Because this is here, the speed of light is in every direction is the same because it's here on the bottom. And then this is the change distance. So in a sense, this light-like intervals are like perhaps properly encoded with this metric. And it actually happens that the Shapiro delay has exactly these two effects. There's the effect of radial lengthening, and then there's the effect of local speed of light in coordinate time reduction. And you can calculate like the proper Shapiro delay by moving along these kind of geodesics. And then this is in some circles it is known that you can create a Flam paraboloid by adding a new orthogonal spatial direction here and bending the space in that newly you have new degree of freedom when you add new dimension to space. So then you can bend the space so that the dr and now this dr prime they are in this like Pythagorean relationship, and you can just simply by surface integral integrate out this form of the surface, how it differs from the flat space-time where there's no mass. And this is called Flam paraboloid, and I guess the problem here is that because this is a light-like geodesic, then no massless particles can travel there. So usually it's not taken as that kind of physical. But in Suntola studies, Tuomo thinks that everything moves at the speed of light. So in some sense, everything moves still along these geodesics. And that is a real thing, this bending of space. And you can then calculate at least light propagator exactly in this Schwarzschild space, but also potentially like matter traveling in this kind of bending space. I will just show maybe 2 slides and then yes, okay. So now the important point here is that Tuomo thinks that these Schwarzschild gravitational factors, he has derived from like zero energy principle this kind of factor here. So it's almost the same, but there's no square root. And now this surface integral results in a different kind of surface, but still the relations are essentially the same. And also I forget to mention here that also this gravitational time dilation can be encoded in this geometric setting and then you get the Newtonian escape velocity or free fall velocity here, as Tom showed, but here it's calculated. And you can then actually calculate what is the coordinate speed of light compared to the coordinate speed of light at the Earth potential. And this is actually encoded, these kind of changes are encoded in time standards currently. So there's these geocentric coordinate systems or coordinate time, and it's actually exactly this that they use. So there's coordinate standards, time standards that actually sort of encode this coordinate speed of light reducing in coordinate time. It's a weird thing, because actually you could here calculate exactly that every dr prime takes 37.7 micrometers per meter down into this gravitational well. And using that surface, you get the exact Shapiro delay and everything correct. So it's, and now I guess Tuomo's idea is that this surface is somehow real, or at least it like warrants this kind of like really serious like thinking, like how does matter move in this kind of thing. I also showed here there's the Schwarzschild solution, but the light geodesic, and then Suntola's model goes differently. All right, but maybe I'll stop here. I have few like slides, but they take some time. Let's make so that I will show them really quickly, and then
Got 5 minutes.
5 minutes.
Yeah.
5 minutes. Okay, I will show them really. So be prepared. Okay. So here's the one way of conceptualizing a general relativity is variable speed of light theory in coordinate time. So Earth goes, it's perihelion and aphelion. All right, the C is defined as such, and it's the proper time. Okay, with this you can calculate the proper time. All right, you can calculate the Schwarzschild critical radius, and they are really small usually. So usually all the gravity tests are made in weak gravity, not thinking about merger of black holes and stuff. And now you can compare proper times through this coordinate time directly. And so the speed of light in coordinate time is slowing down. And this is actually observed in pulsar studies. So pulsar studies, they add the Romer delay, which is the delay caused by constant speed of light. Then they add the Shapiro delay, which has the lengthening of the radial dimension, and then the lowering of the coordinate speed of time. And then they add the Einstein effect, which means that the local standards are changing depending on where you are in this gravitational potential. And this has been observed. So they actually tell that the fact that the Earth is moving on an elliptical orbit around the Sun, and hence at varying distances, means that every clock on Earth experiences a varying gravitational potential throughout the year. This leads to seasonal changes in clock rates that affect all clocks on Earth simultaneously. Astronomy can hence provide an independent time standard that is unaffected by effects on Earth or the solar system. And pulsars are involved. And now this is the mathematically and scientifically important thing, that if you go to those studies how the Einstein effect is calculated, they use usually Moyer, which is from Jet Propulsion Laboratory. They refer to Misner, and they use this metric, this as a time dilation term. And they tell that this is a Newtonian approximation, and you can see it because if you go near the critical radius, then you can go imaginary. So this is already an approximation. Then they approximate it with this in that same paper, because you are in so weak gravity. Then I have also seen the Schwarzschild version, where there's the inverse of this Lorentz term. And now this is a Suntola proposition, is this. And now this is the difference between du and gr. and there are different time standards already. So already it's defined sort of in coordinate time. The coordinate time is defined already variable. So you have terrestrial time, you have geocentric coordinate time, you have barycentric coordinate time, and all the astrophysics of celestial mechanics is done in these coordinates, which you then move back to local coordinates, local proper times, by using those Shapiro delays. And you can now try it. So this is the gravitational time dilation. I consider this empirical. So there's circular layer orbital height around Earth. There are, for example, GPA here. Then there's time dilation in microseconds per day. So the clocks go like they are experienced as physically going faster, because you have to set it down, set it differently when you bring it up, and it has accumulated different thing when you get it down. And you can actually draw these curves, this total curve, using this. So it's just a fractional change in the frequency is such that you consider the clock that you are thinking at distance. So then it's clicking coordinate time. Then you bring it back in gravitational state to that state where you want, and it decreases down. Then you give it the orbital velocity, so the kinematic term, which decreases down even further. And you simply divide it by the same procedure done to your reference clock. So you bring your reference clock to the coordinate time, you bring it down to the Earth surface, you bring the kinematic term, which is, they are always calculated, it's kind of non-rotational inertial geocentric coordinates, and you get this exact here. I didn't even plot it here because I have plotted it so many times and you don't see any difference. And this is completely different way of dealing with gravitational time dilation. And it might work just because we are in weak gravity, but it might also work because there's something essential about gravity going on here.
So is this the DU picture?
Yes, yes. Oh, this is from an online encyclopedia called Time Dilation. So this has been seen by thousands of people, and this is generated by like standard Dirac.
Okay.
And this brings totally the same.
So the exact same.
Exact same. In microseconds without any extra parameters. I just put the Earth mass and the mean radius. You get the exact same. So in a sense, this formula could be used in school already because it's like a phenomenological model at least. But it might also tell us something about gravity. And Suntola proposes that actually that rest energy, because there's mc, then the m is modulated by this, and the c is modulated by this. So it's like a sort of like factorized gravity. But it's it's completely different to using a metric and different. And maybe I'll show you this still if there's 2 minutes. So 1 minute. Because this McCarthy has most wonderful title, former director of time at US Naval Observatory. And there's how time measurement has advanced. And now Suntola proposition is such that this is from the picture. There's always the quartz oscillator and atomic resonator. So the atomic resonator, you can look at the formula. It's directly proportional to C. And these other terms here, they don't have C if you take the Suntola proposition seriously. So actually when the coordinate time C decreases, then the frequency decreases proportionally. And you won't see it in proper time because you are using this clock to define the standard. And also the quartz oscillator needs to be in the same sync. So the speed of propagation, it's this, so it's also proportional to C. So it will stay exactly in sync. And then the masses are here in this Rydberg constant. And the Suntola proposes that mass sort of splits into this kind of a rest energy frame, and then this ordinary like relativistic mass. And you could see that at least algebraically this could be correct, because then because the Rydberg constant is proportional to Bohr radius, and Bohr radius is a characteristic length of a condensed matter. So actually, at speed, if the rest mass decreases, then the Bohr radius increases, and then this characteristic, this length in quartz crystal increases, and the frequency drops. But it's completely, so this is like a physical way of thinking time dilation, but the clocks actually expand at speed, and that's why we see what we see. And if we wouldn't have relativity, then that would be like, we would need to explain why we see the frequency drop as we see.
Okay.
Okay.
Yeah. Thank you.
Sorry
very much.
for.
Good. Any questions? There were a few. Yeah.
Thank you. I think on one of the previous slides you had
Yes.
a different formula for sorry, stay with that slide for now, but you had
Okay.
a different formula for time dilation.
There's
Is
no
that-
time dilation here.
Right.
Yes, yeah, because here you just then multiply these. So I haven't written them here. These are like exact formulas from the research publications.
In the dynamic universe model, does time dilation work differently to general relativity?
Well, yes, because the Schwarzschild radius or the critical radius is different.
Yeah. So my
Yes.
question was, of the right-hand side of your graph with year there's obviously been considerable improvements in time measurements. Just down the road outside London, National Physical Laboratory has some very accurate clocks in there. I'm just wondering if we are now at the stage where you could actually do some testing with some of the modern atomic clocks.
Yeah, but at least these two, you can do testing because that's observed, that frequency drop. But there are different different explanations to that. There are explanations where the speed of light doesn't change because you always measure it the same, so because the standards change. And then it's due to the photon getting energy when it's dropping the gravitational potential. But then if you calculate in coordinate speed of time, the speed of light, then the speed of light is less here, so that when the coordinate frequency stays the same, then the waves tighter together, and the frequency increases seen, the engine increases seen. So they are like dualistic. At least in that kind of like scalar form. But bear in mind this, the isotropic of space and that kind of things, they are difficult problems.
Okay, so have I misunderstood? Those two cancel out, so you have the same
Yeah.
observable.
Yes, they do. But in really strong gravitational fields, the situation would be completely different because here the critical radius is half of the Schwarzschild radius. And it's like a completely different picture of the black holes, and who dares to go there?
Thank you.
Yeah. Anybody?
So, with you talk about black holes. Could you potentially use cosmological data of like the lensing of light around the black hole at the center of the galaxy to compare the two?
Yeah, but I'm not familiar with how long are the distances, because you have these images of black holes. How large is the critical radius in there? Because you have to be really, really close to get those things. And also when there are these black hole mergers and these gravitational waves, I don't know how strong gravity, how close, in what region they are made, those. Because if they are made quite far away actually from the critical radius, then the physics agree. Or actually, one can see that they could agree. Yeah.
So basically, what I'm getting from this is that GR already predicts a change in the speed of light in different reference points, or is a change
Yes.
in the yes.
Yes, it looks
But
like
it's not quite the same one as you get from the DU picture, but it is equivalent for the gravitational fields. And
Yes.
you then need further testing to figure out which is the correct.
And there's also the question of making nature understandable in a sense that there's a possibility for pedagogy here. Because if it's the same, then you could have like really simple models. For example, these models usually they are much more because they are like in some form, so there are these approximations made, and they are difficult to understand. But here it's like almost classical physics. You just think that your frequency has dropped and you divide by normalize by that, and there's no reciprocity here. And in general relativity, there are no reciprocity. So
Just a final thing, I know Trevor mentioned in the very first talk that in ADS you get a sort of equivalence between the DU and the GR picture, with the bouncing out of the gravitational force of the expansion. So if you ran this in ADS, would you get the same kind of time dilation or the same kind of speed of light variation for DU and GR? Or
for which empirical?
if you ran it in ADS space.
I don't know. Yes, there are a lot of physics is complicated.
Yes,
there are a lot of
no,
empirical
no,
data.
I in the past stuff I wish I would go research.
Good. Anybody else? Right. So thank you very much, Delmo, again. And